Here we have a tiny amount of steam with an initial temperature of T naught S greater than 100 degrees Celsius is added onto a container that is an aluminum calorimeter with liquid water. The aluminum calorimeter and liquid water is at an initial temperature of T naught. We are asked to determine the expression for the latent heat of vaporization when the system reaches a thermal equilibrium with a temperature of Tf. All the steam turned into water, and you're asked to graph the energy versus temperature of the steam. The following values are given: mass of the aluminum, mass of water, mass of the steam, the specific heat of aluminum, the specific heat of steam, and the specific heat of water. And you're also asked to determine the range or range values of the T naught and T final. So we have the system here. So you have steam being added onto the aluminum and water that are initially at T naught. So we consider the energies that are present. So you have the energy or the heat coming from the aluminum, then the heat coming from the water, this water here, the heat coming from the steam. Of course, the problem states that the steam has converted into water, so we need to add the latent heat of vaporization expression that is given by this expression here. We note that we assign a negative value here since the steam has turned into water. That means it is losing energy. Then, since after this process the steam has turned into water, we add this expression here, wherein the mass of the steam is being moved towards from the temperature to the final temperature, as shown by the expression here. So by conservation of energy, which states that the sum of all of this energy must be equal to 0, then we can relate all of them by this expression 2 here. So you have Q from the aluminum, Q from the water, Q from the steam, minus QV, the transformation part of steam into water, and the transformed water being moved towards the final temperature. Substituting the values or the expressions that we wrote earlier, we have this expression here from the aluminum, from the initial amount of water, from the steam, the transformation, and the mass of the steam being moved towards the final temperature. So we know that for the aluminum can, it starts from an initial temperature T naught, then towards T final, so there's no transformation here. Similarly with the water, or the initial amount of water, it starts from T naught and it moves towards T final. For the mass of the steam, so we know that it's initially at T naught S, which is greater than 100 degrees Celsius, so we have to move it first from T naught towards the 100 degrees Celsius, wherein the transformation will occur. Then we add the parameter for the transformation here, wherein we have our parameter in question, which is the latent heat of vaporization. Then upon the transformation, we then convert the steam into water, so we have to use the specific heat of water now to move from 100 degrees to the final temperature, and these are all equal to 0. Now rewriting the expression, we arrive to this term here. Okay, you can also simplify this further by taking these two parameters, this one, and divided by ms. Okay, and you arrive to this expression here. Now let us look at the graph. So we know that initially T naught S is greater than 100 degrees. So it has to be somewhere greater than 100 degrees. So the system, the vapor or the steam, is first lowered from T naught S towards the 100 degrees Celsius. So we see here the energy, it's losing energy. Then after that one, the system, the steam, is now converted into water, and it has to go through this process called um, the condensing aspect. Okay, so where we apply the minus mLV here. Then after it reaches or completely being transformed, now at this temperature 100 degrees Celsius, it is then lowered to the final temperature. Okay, here when from 100 degrees it is being lowered. Okay, for the ranges, we know that the T naught must be greater than 0 degrees Celsius because we have initially liquid water. Okay, and it cannot be in ice form. So that means the temperature will be around greater than 0 degrees but less than 100 degrees Celsius approximately. For T final, it's obviously less than 100 degrees, but since the energy is now being transformed into water, so it must be somewhere here. Okay, so that final temperature is of course being raised to some point here. So it cannot be T naught or less than T naught, but rather it's greater than T naught. So these are the values.